So the Hardy-Weinberg theorem represents or describes the allele frequencies that are present when evolution is not occurring. So that's the main thing you have to remember about the Hardy-Weinberg theorem, is that evolution is not occurring. And there's a few conditions that must be satisfied in order for the Hardy-Weinberg theorem to be valid. And that includes large population size, no natural selection, no mutation, no gene flow, and mating must be random. And the reason for this is, as you'll recall, these are basically all of the mechanisms of evolution. Small population size is genetic drift, natural selection is a mechanism of evolution, mutation, gene flow, and sexual selection can all affect allele frequencies. So again, the Hardy-Weinberg theorem describes allele frequencies when evolution is not occurring. More commonly, it's shown as the equation p squared plus 2pq plus q squared equals 1. And I'm just going to go through a quick proof of why this is evident that evolution is not occurring. P squared, or P is one allele for the color gene that I'm going to be using in this example, and then Q is the second allele at a particular gene. And this P and Q are used because this Hardy-Weinberg theorem is mainly applied to diploid organisms that have two alleles for one gene. So in this example, we have 4 generations of butterfly. The F1 generation here, and suppose that half of the F1 butterflies are of the genotype BB for dark blue, and half are WW for white. And then in the F2 generation, we're going to be having a mixture of, or actually all of these butterflies in the F2 generation will be BW genotype, and then we'll have F3 generation here, which will be a mixture of those 3 different genotypes, and then the F4 generation here. And the reason why this occurs and why this will end up eventually satisfying the equation that I wrote up here at the top is that if the gametes that are produced by the F1 generation can be predicted by a simple Punnett square. So if you have BB and you have WW, all of the gametes that are produced from this, or half of the gametes that are produced from the F1 generation are going to be B, and the other half are going to be W. When you cross these and come up with the result in the next generation, you're going to have something like this Punnett square here, where BW ends up being the genotype for every butterfly in the F2 generation. And so in F2, all of them end up being BW genotype. But as you can see, there's still 50% of the alleles are B and 50% are W. And so these gametes then go on to the next generation, and you end up using another Punnett square here, and you cross all of the heterozygote genotypes from the F2 generation, and you get 50% that are homozygous for dark blue, 50% that are homozygous for the white genotype, and then 25% and 25%, totaling 50% that are the intermediate phenotype. So, but in the same generation, if you look at this Punnett square, you still have 50% that are the B phenotype, or 50% allele frequency of B, and 50% that are for white. So again, these move on to the next generation, and the same thing occurs. You can do the exact same Punnett square we just did for the 3rd generation, and you get homozygous BB, homozygous WW, and then a mixture of the two. And from that generation forward, it's going to continue to persist. The allele frequencies from the very first generations are consistent. It was 50% of B and 50% of W from the very beginning. And I just wanted to go through this little exercise to show you that what the Hardy-Weinberg theorem actually means. And if you look at this equation, you take the initial allele frequencies, and let's just say in this example we use B and W instead of P and Q, and you have B squared plus 2BW plus Q squared equals 1. So the initial frequency of alleles in the F1 generation was 50%, so this ends up being 50% squared plus 2 times 50% times 50% white plus 50% squared equals 1. So this would be 0.25, and this would be 0.5, and this would be 0.25 equals 1. So in this example, it has a large population size. None of these other evolutionary mechanisms are occurring, and Hardy-Weinberg conditions are satisfied, and these are the proportions of alleles that will persist in each generation if evolution is not occurring. And if for some reason we're to give you the allele frequencies other than these numbers, it'd be safe to assume that either one of these conditions is not being satisfied, or alternatively evolution is occurring.